All right, so let's take a look at this linear factorization example. This is the one that we did in class, so if you're absent, this would be a good video to watch. And in this problem, this is actually number 32, I think, from the chapter 2 packet. You're supposed to find all these zeros of this quintic polynomial, and then you're supposed to write f of x as the product of all the linear factors. Now, there was a theorem that you learned last year called the rational zeros theorem that says potential rational zeros, would be factors of the constant over factors of the leading coefficient. So factors of the constant term over factors of the leading coefficient. So you can do this if you want. That's going to be plus or minus 1, 2, 4, and 8 over plus or minus 1. These don't tell you what the actual zeros are. They just tell you which zeros, if there are rational zeros, they have to be one of those combinations. But what I would rather you guys get in the habit of doing, because you don't really know which ones are going to work unless you look at a graph anyway, or just test all 8 different possible zeros you can get out of this. So instead, you can graph it. So let me see if this will work here. So I'm going to open this up, clear y equals, and let me type in the function x to the 5th minus 3x to the 4th. Uh-oh, let's do that again. X to the 5th minus 3x to the 4th minus 5x. Oh, geez, I'm doing it again. Minus 5x to the 3rd plus 5x squared minus 6x plus 8. Okay, and if you graph it, you're not going to get the greatest window here. You can tell that it comes up first, then goes down, then goes back up. So what I'm going to do, I figure I got to go pretty high up on the y's and pretty far down on the y's as well. And I can zoom in a little bit on the x's. So, and I've already worked this out in advance, but you can do a little bit of trial and error. And here's a good window that works. It's negative 3, 5 by negative 1, 10, 30. And I'll go by tens on the y scale. So here's a good picture of that graph. Okay. So let me actually copy this picture. And let's see here. I'll move this to the side. Edit, copy, and paste this over here. Okay, so there's my picture. Oop. All right, so I'm going to minimize this window. So in this, I'll zoom in a little bit. Okay, and when you draw a sketch of yours, make sure you note the window that we used. In this case, 3, 5, negative 3, 5 by negative 1, 10, 30. Okay, so there's my window. And this gives me good ideas as to what the zeros might be, the real rational zeros might be. This looks an awful lot like x could be negative 2. So I'm going to write looks like x equals negative 2. And this 0 looks like x equals 1. And this 0 looks like x equals 4. And we don't know for sure, but those are awfully good candidates. So, you know, on a test or on homework, if you want to skip this and just go straight to this, that's totally fine with me. So in fact, I'm going to erase this over here. So delete that. Okay. All right. So our candidates for rational zeros are going to be x equals negative 2, x equals 1, and x equals 4. All right, so that also means that x plus 2 and x minus 1 and x plus 4 would be, could be factors of f of x. Okay, so how do we check? All right, well, let's see if x equals -2 is a factor of x, right? So in order to do that, I want to basically divide f by this and see if it works. Now, since that's a linear term with coefficient 1, we can do synthetic division. And so you could plug in -2 into f using the remainder theorem and see if it's 0, and that would work too. But let's take a look. So, because I feel pretty good that that point right there is -2. So the coefficients are 1, -3, -5, 5, -6, and 8. And I am checking x plus 2, so -2 goes here. It's exactly the same as the 0. So I'll work this out. That becomes negative. That becomes 1, multiply, get -2, add -5. This is 10, add straight down, get 5, multiply, -10, add straight down, -5, multiply, we get 10, add straight down, we get 4, -8, and 0. And remember, this is important. The remainder is 0. That's a good thing. That means that x plus 2 evenly divides into f of x. Okay, so at this point, since -2 is a 0, that means that x plus 2 is a factor of f. And that also means that all this is what's left over. So 4 is the constant, -5 is my x term, this is my x squared term, my x cubed term, my x to the 4th term. So this is now, I can write it as this, minus 5x cubed plus 5x squared minus 5x plus 4. All right, so that's what we have now. Well, that's still kind of ugly to factor, but I also have that x minus 1 probably goes into it. So instead of taking the original problem again and putting a 1 there, I'm going to just take what's left over and do it with that instead. So I'm going to try, so over here we tried x equals -2 is a 0. So now we're going to try x equals 1 is a 0. But instead of trying it on the original, we're going to try it on what's left over, because if it factored into the original, it should still factor out of the what's left over. So my coefficients there are 1, -5, 5, -5, 4. And this is 1 right here. So do synthetic again, multiply, add -4, multiply, add, multiply, add, multiply, and add. And since the remainder is 0, that's good, right? Because if the remainder is 0, then I know that x minus 1 is a factor. So now I can write f of x this way. I can say x plus 2, that was the original one. Now I factored out an x minus 1, and what's left over is 1x cubed minus 4x squared plus x minus 4. So it's x cubed minus 4x squared plus x minus 4. And if you wanted, you could then take this guy and try your last 0, which is 4. Or you could recognize that this happens to be one you can factor by grouping. So we'll do that. This is x plus 2, this is x minus 1. And then this, I can factor out an x squared from the first two terms and get x minus 4, plus 1 x minus 4. And so then, if I leave these first two terms untouched, this will turn into x squared plus 1 and x minus 4. And then, so right now, this is a product of linear and quadratic terms. But I can turn this into a linear term, into two linear terms by factoring it. And maybe you remember it's x plus I, x minus I. But if you don't, well, you're just trying to figure out when it equals 0. So x ends up equaling, x squared equals -1. So x equals plus or minus I. So then you know you've got x plus I, x minus I. So this guy here becomes x plus 2, x minus 1. I'll do the real ones first. So it's x minus 4 And then this turns into x plus I, x minus I. Okay, so we've got 5 zeros, 5 complex zeros, which are x equals -2, 1, 4, and plus and minus I. We've got 3 x-intercepts, which are the real zeros, x equals -2, 1, 4. So it turns out in our graph, all 3 of those actually were exactly what we thought they were. And then 2 non-real zeros. 2 non-real zeros. X equals plus or minus I. Now this term right here, this version of f of x, where it's fully factored into linear terms, that's the linear factorization of f. The one right before it, that's also f of x. This one in particular, this thing right here, that's also special because the linear terms are already reduced as much as possible. And the quadratic, if you leave it in that form, all the coefficients are real, but if you actually factor it, you get these imaginary terms instead. And sometimes people prefer only real coefficients. So this version of f of x is also called the product of irreducible linear and quadratic terms, or let's say quadratic factors. And the reason you'd say that it's irreducible, well, the linear terms are already as simplified as possible. If I tried to factor the quadratic, you get imaginary numbers. So irreducible linear and quadratic factors with real coefficients. And so if you come across a problem that says something like this, that's what it means. No I terms. Multiply those conjugates together, and then you'll get an irreducible quadratic instead. Okay, hope that helps, and I'm done.